On the last lecture, we introduced determinants and have proven the most important facts about them, but with exception of one fact. And for many of you, so not for many, but for at least for some of you, when during yesterday's office hours, this was the problem. So this is why I will formulate this important fact as a lemma. So essentially, for each n, if there is an n, okay, let me write it like that, it's better. A determinant of an n by n function matrix, then it is unique. Essentially, if you define any function which satisfies the definition of the determinant, which is essentially it's just the function which maps from the space of n by n real matrices onto the real line, right? So essentially it takes a matrix and returns that number, right? Then also it satisfies all 4 requirements. So which means that its determinant does not change if you apply elementary row operation number 3 to the matrix. Determinant is multiplied by -1 or changes sign if you exchange 2 rows, right, of the matrix, and determinant is multiplied by the corresponding scalar if you multiply any row of the matrix by this scalar, right? So, and also that determinant of identity matrix is 1. So if you have you introduce the function which satisfies these requirements, then this function is unique. So it doesn't matter how you will introduce it, essentially. So this function will give you all these different definitions will give you the same result. This is why, for example, you see, first I introduced this definition and then said that, okay, this is how we can compute it using Gaussian elimination. We bring it to the row echelon form and then multiply elements on the diagonal, right? So what is interesting that from here it immediately follows, so that because we can always bring, doesn't matter how I will introduce it, so if it satisfies all these conditions, I can apply these elementary row operations, bring it to the row echelon form, multiply elements on the diagonal, that's it. So this will be the value of the determinant. It doesn't matter how I determine, how I define this function. So for example, in one of your problems for your homework, so you needed to show that, so we were introducing determinant of the product of 2 matrices where this is given. We were introducing and non-singular. We were introducing it as essentially, no, not like that. So we were introducing the determinant of an arbitrary matrix T as Ts over S. And then you were asked essentially to show that this is a determinant function. So to show that even if you apply all these elementary row operations to the matrix T, the result will stay the same, essentially. And then the statement is that it doesn't matter how I will introduce my determinant function. So this lemma tells you, it doesn't matter how you will introduce it for a given S, which is non-single, right? So the result will be always the same. And the proof of this lemma, as I said, so is the following: that because we can perform Gaussian method, so Gaussian elimination, to bring to the reduced row, not even reduced, just row echelon form. It's enough. So then a result has to be always the same, because we will always bring to the echelon form. So it will be the same echelon form. That's it, of the matrix. Okay, then you can also introduce the determinant, and this is where essentially this is this Laplace extension appears. So you can introduce it through so-called permutations. Okay. Let me first give the definition. Let V be a vector space a map F, which maps Vn to the real line, is multilinear, if first essentially if you add corresponding two rows to two vectors. So let's say like that, yeah, because we are working on the vector space. If you consider n vectors in this vector space, and you add two vectors, then these will be equal to this. Essentially, it's linear with respect to addition of two vectors here, and two, if you will multiply any of the vectors by some scalar, then you can factor it out. The scalar. And this has to be true for any VW belonging to the vector space and K belonging to the set of real numbers. So essentially, idea is the following. you apply this function, so it's defined on n vectors from this vector space. This is why it's n here, like a power, but this is not power. So it means that you apply it to n vectors of the vector space, and it produces just the number. So function takes n vectors and produces a number. So, and function has these properties of, it's called multilinear. So,
can I ask a quick question, Professor?
Yeah, go ahead, please.
These vectors v and w, are they row vectors like the other ones that we defined?
So you see, for now, vector space is just any vector space. So as we know, row vectors, they also form a vector space. So we can use row vectors as a vector space of row vectors of some number of some metrics as as an example in this definition. So yes, this is exactly essentially the statement. The next statement of the next lemma is practically the answer to your question, right? So determinants, they are special case of multilinear function. Okay? Is it clear or not?
Yeah.
So you see, here V is an arbitrary vector space. So I introduced this definition of the multilinear function for an arbitrary vector space. For example, I can introduce a function over space of polynomials, right? Or space of continuous functions. But if we consider a special case of row space, for example, right? Of n dimension, of n by n matrix, right? In general, n by n matrix. So then, yes, it also will, this definition also will be applicable. And exactly what we are saying is determinants are multilinear. So pay attention. In order to prove that determinants are multilinear, so this is already in the definition of the determinants, right? So essentially, when we apply when we apply elementary row operation number 2, multiplication of a row by a scalar, right? Pay attention, in the definition of the determinants, it's not required that the scalar is non-zero. So then you are getting essentially immediately this second property, right, for multilinearity. So now for the case, for this case, for one, so essentially we need to prove it. So what all we need to do, we need to verify this property 1. So, and there are 2 cases. Probably it will help for those of you who had troubles with this problem, where you needed this problem, where you needed to show that this is a determinant. Okay, so if the set of other rows, cases. First one, if the set of other rows rows 1, I minus 1, I plus 1, n is linearly independent, then all three matrices are singular, linearly dependent, sorry, dependent. All three matrices are singular, and it works. So what particular works? This thing. So if we have linearly dependent rows, so this is ith element, and this is ith element. So essentially, if other rows are linearly dependent, these rows, all but which we are working with, that we know that if rows are linearly dependent, then determinant is equal to 0. So then this is equal to 0, and here we will have 0 plus 0, right? So it's obvious. Okay, therefore, now we need to consider second case, that all other rows are linearly independent. Okay, so then let's make a basis. By adding one more vector. Because we have n-dimensional space, right? So we have n rows and all others are linearly independent. Let us find the row which is not covered by the previous linearly independent rows, and it will form a basis. So, and let us express our V with respect to this basis. So essentially it will be V1 row 1 plus and so on, plus Vi minus 1 row I minus 1 plus beta plus Vi beta, right, plus Vi plus 1 row I plus 1 plus and so on plus Vn row n. And the same thing, we represent our vector W with respect to the same basis. Wi minus 1. Wi beta plus Wi plus 1 rho I plus 1 Wn rho n. Okay. Now, when we add corresponding V plus W, we will get V1 plus W1. Oops. Rho 1 plus and so on plus Vi plus Wi beta plus and so on plus Vn plus Wn rho n, right? So now, if we will consider left side of our expression 1, so essentially expression 1 was, let me remind you, this one. So this is the left side, right? So I'm applying my function, my determinant function to here. Okay. So then determinant of row 1 v1 plus w1 row 1 plus and so on plus vi plus wi beta plus.
Can I ask, I feel like I'm a little confused as to why you include row 1 on its own and then also have v1 plus w1 row 1. Are you including all of
No,
the?
no. It's, you see, I'm just I'm considering this here. So you remember, this is what I need to do. I use all other rows, right? They stay here. They cannot go anywhere, right?
Oh.
So and then I just expressed this sum, each vector and their corresponding sum through the basis of all rows and plus extra vector to form the basis, right? Because I know that these rows are linearly independent. Because for linearly dependent rows, everything is obvious, right?
Okay, so you're just doing that and putting them there for the proof.
Yeah, yes,
okay.
Exactly. So so you see, I just represented this sum as this linear combination, right? With respect to the corresponding basis, right?
Yeah, okay, thank you, that clears it up for me.
Okay. So, and so on till row n, right? So essentially all I need, I just expressed this through all other rows and this extra vector which I added to form the basis, right? Okay. So by the definition of the determinants condition, so the first condition which we have for determinant, so you remember we can consider, so we were considering elementary row operation number 3, replacement of a row with the sum of the same row and multiple of another row, right? So the first condition, so the determinant doesn't change under elementary row operation number 3, right? Which is row I is replaced by row I plus alpha row J I not equal to J, alpha is any scalar, right? Right? So I know that I can add, for example, to here, I can add, let's add, so determinant stays the same under this operation, right? So let's consider negative v1 plus w1 row 1. Let us add it to here, because determinant has to stay the same, right? So what we are getting that v plus w, which is this, it's v plus w, right? Minus v1 plus w1 row 1. So essentially I subtracted this term. So will be everything else V2 plus W2 row 2 VI. Oh, and nobody corrected me. So no vectors, of course, it's just coordinates. VI plus WI beta Vn plus Wn rho n, right? So once again, under elementary row operation number three, determinant has to stay the same. And I can continue subtracting all other rows multiplied by the corresponding coordinates, right? And determinant has to stay the same. So I can eliminate this term. Essentially, I can eliminate everything else but that, because this beta is not between other rows, right? So as a result, determinant of row 1 V plus W row n will be nothing else but by definition of the determinant, so we can bring it to this form. Vi plus Wi, this beta rho n, just this. But then using the second, another property of the determinant, or you can say using this rule, which is already there in the determinant, I can factor out the corresponding scalar, which is this one, and it will be Vi plus Wi determinant of row 1 beta rho n, just this, right? But then I can write it as determinant, oh, sorry, Vi determinant of row 1 beta rho n plus Wi on the determinant of row 1 beta rho n. But this is sum of the determinants, right? And I can bring this back inside using this property again, this one. So because I will use it just in this direction, this equality. And this I will bring there. And then I will reconstruct back V and W by adding these, then these, because I know that determinant doesn't change under elementary row operation number 3. And I essentially reconstruct my V and W inside. And then I will get determinant of row 1 V row m plus determinant of row 1 W rho n. That's it. Is it clear or not?
I did have one question.
Yeah, go ahead.
So you had kind of said it, but I don't think I quite understood about how you're able to subtract all of the values except the vector with beta.
Beta. Yeah, because essentially what I'm doing when I subtracting from a row or adding, doesn't matter, this expression, I'm replacing a row I, right, with a sum of this row and the multiple of another row. You see, I is not equal to 1, for example, so, and then this is multiple of another row, right? And I know that by definition of the determinant should not change, right?
Yes, that's correct.
This is why I can do this using all these row 1, row 2, and so on till row n, but because beta is not between the rows, right? So I cannot eliminate this particular term, right?
So what do you mean by beta is not between the rows? Like it's not in the matrix?
Okay. How have I got my beta? I started from the fact, so let us suppose that all our other rows, but the ith row, right, are linearly independent. How many of them? So we consider matrix of n with n rows. So if I consider all other rows but 1, so how many rows are there?
N minus 1 that are going to be
N minus 1, right? So, but I know that for if I consider vectors, n-dimensional vector space, or a vector space collection of n vectors from the vector space, right? So this is in general n-dimensional space. So I need to add another vector to form a basis, right?
So you're saying that B is going to be linearly independent, or beta?
Yes,
beta.
of course. Of course, beta has to be linearly independent. Otherwise, they will not form a basis, right?
So then that's why you aren't going to subtract it from the other side.
So essentially, I'm subtracting all other. So here, you see?
Yeah,
then,
but I mean.
So this is another basis vector, right? Ith basis vector, right?
Yeah.
Okay. So I have all other rows, right? So these ones, these are other rows, right? And I'm subtracting, just essentially getting rid of them, of these corresponding terms, right?
Yeah, and because in a basis, if you have linearly independent vectors, you don't have to use them to describe the basis anymore, right?
I mean, I don't want to describe the basis. So I essentially, I just, I represented my arbitrary vectors from the vector space V and W, right? I represented through the rows, other rows, and this one basis vector which I needed to get the basis, right? So because I have to have n vectors in the basis, right?
Mm-hmm.
So I just added one which is linearly independent with others. So, but the thing is that I can get rid of all these other things inside of the determinant. Pay attention, only inside of the determinant function, because by definition of the determinant, it stays the same under elementary row operation number 3, right? Replacement of a row with the sum of this row and multiple of another row. This is exactly what I'm doing when I'm adding these. So essentially, this term, this first term, right? Just with negative sign. I know that determinant will stay the same under this operation, right?
Yeah, I understand.
But I don't have this beta between other rows, right?
It's just itself.
Yes, it's just itself because it's linearly independent with other rows, right?
Okay, I guess that's what I had asked. Like, is it because it's linearly independent that you can't subtract it?
Yeah, because you see, elementary row operation number 3 requires you replace a row with the sum of this row and multiple of another row, right?
And beta doesn't.
And another is important, and beta is contained only inside only in this row, right? And it's linearly independent. You can't express it through other rows, right? Because it's linearly independent. So you cannot use elementary row operation to eliminate this term. So this term will stay, right?
Okay, but by the statement that you had below, it seems to look like VI plus WI beta is going to be equal to the linearly independent rows.
No. You see,
row one,
VI,
row two,
VI plus WI beta, right? It stays. I cannot get rid of that because it's linearly independent with other rows, right?
Yes, but I mean, because you had when you were taking them and subtracting them, just like maybe one statement above it that you just circled.
Everything else but this I can eliminate because it contains another row multiplied by some scalar.
But does that equal sign statement mean that VI plus WI beta is equal to?
No. Okay. So what? So I shouldn't cross it here. So I did it just for shortness. So when I said that, okay, so this is how I can represent it, right? You see? So I subtracted proportional to row one term, right? And then I have what is left, row two, and so on, right? And I'm just saying that here in this expression, so what I have done, I eliminated this term, right? And I can eliminate all other terms in the same way, but this term proportional to beta. Okay?
Okay, thank you.
So, and this term will stay like that under determinant sign. Pay attention. The thing is that determinant, by definition, does not change under elementary row operation number 3, right?
Yes, that's right.
So that's it. So essentially, after that, what I'm getting that I'm getting determinant of that, but then using another property of the determinant, or you can say another property of multilinearity, I can factor out this coefficient, right?
Yes.
And then I can split this into two, sum of two terms, right? And then using exactly the same property, I will put it back. This,
and is it that?
Yeah.
So for this, it's VI. It would be VI times the vector beta, but you just wrote the vector V and the vector W. Is that?
Wait a little bit. Right. So you agree that I can get this VI and WI in corresponding determinants, right?
Yeah, that's one of the properties you described.
Yes. And then I know the determinant doesn't change under elementary row operation number 3, right? So what I can do, I can add here V1, row 1, and it will not change, right?
Yes.
And then I can add V2, row 2, and so on till Vn, row, oh, no. Here, each, yeah. Vn, row n, right? I will add it here. And it doesn't change the determinant, right?
Yeah, because they're all just linearly.
Yeah, because these are different rows. But then have a look what I've got. I've got exactly V, right? Because I added this term, not this. This was already there with beta. But all other terms I can add. And then I reconstructed my V, right? And the same I can do with W here. And I will reconstruct W. So the result, this is what I'm getting in the end, right?
Okay.
Is it clear now?
Yes,
Okay.
thank you.
Yeah, so this is the idea. So I'm just bringing it to this form. Okay, so essentially, I can introduce another definition. Okay. And n permutation is a function on the first first n positive integers. So it's phi 1 n 1 n. That is 1 to 1 and on to. So what does it mean? It means that I start from some set, let's say 8. 1, 2, 3, 4, 5, 6, 7, 8. And then, because it's 1 to 1 and onto, so essentially I can permute these numbers in any order and get, for example, something like that. 2, 1, 4, 3, 6, 7, 5, 8. So permutation, but the thing is that because it's 1 to 1 and onto, I cannot add any numbers and I cannot throw away any numbers. So I just change the order of them. And then essentially idea is that determinant of a matrix A can be represented as sum all possible permutations of 1 to n sum, and here is negative 1 to the power sigma of phi. I will explain what is sigma of phi. And here is A1 phi 1, A2 phi 2, A3 phi 3, and so on, multiplied on an phi n. So sigma of phi is the number of pair exchanges swaps to get permutation from 1, 2, and so on till n, ordered numbers. So this is essentially, if you need just one permutation, then you will get negative 1 in front. If you need two permutations, two pair swaps, you will get positive 1 here. And then you can prove that your determinant is this. And already from here, you're getting nothing else but Laplace extension.